Hey, scholars, welcome to Chapter 7, or Lab 7 for Chapter 7. Uh, we have a little ways to go, so let's just go ahead and get going, all right? All right, so for the objectives, just take a look. Yeah, the course objectives have been largely the same, okay? Uh, but the learning objectives, we need to sort of talk about these for a little bit. All right, so you want to be able to create a SAS program to compute and display interval estimations. Okay, so this is what we're focused on, interval estimations. Okay, you want to be able to properly read and interpret SAS output. Okay, uh, and then you also want to properly report interval estimates. Okay. And then here, this is, also pretty crucial. Uh, it's important that you're able to, look at the results of a sample, look at the estimates that it gives you, and say, all right, are these good estimates or poor estimates? Okay. All right. So like I said, in part one of the lectures for chapter 7, like I said there, um, you know, if you don't have the population data, you can't really evaluate, you can't directly evaluate or, know with a high degree of confidence that how well or how poorly your sample performed. Okay. All right. Um, but there are other things you can take a look at, all right, and come to a conclusion about the quality of your sample, all right, the quality of your estimates and the quality of your sample, all right. Um, so it's going to be really important to pay attention to this, especially this last part, okay, because this is absolutely crucial. This is the thing that's going to separate, someone who can read statistical data to someone who can actually evaluate it. Okay, and that's what you need to be able to do. Probably more, you need to be able to read it, and you need to be able to evaluate it. Okay, and so that's why we're gonna, that's why I'm gonna put so much focus on those last things. Okay, all right. What else? All right. So key terms. Um, Alpha level is going to be a term that you see quite a bit in chapters 8 and 9. Okay, you're going to see a little bit of it here, and I'll talk about it a very little bit here. But when we get into chapters 8 and 9, you're going to see it a whole lot. Okay, everything else is pretty, stuff we've already mentioned before. Okay, in the lectures. Okay, so here's your, at least the first part of your SAS program that you're going to use for Lab 7. All right, the first thing we need to do is create a population. Then we need to draw a sample, and then we need to get statistics for uh, the population parameters. Okay, so for the four variables we have listed here, right? And then we need to get statistics from the sample data on those same four variables. Okay. All right. And so when we get all that, we're going to put it into a table format. Okay. And then take a look at some stuff. All right. And then I'm going to show you how to evaluate the quality of your estimates and your overall sample. Okay. All right. All right. So the first thing we're going to do is create a population, right? So we're going to use the statement data, pop population data. All right, and then we're going to say call stream init. So we're going to set 49 as our initial seed value, right? So SAS is going to start drawing, random, selections from our sample, right? Starting from that number 49. So it'll just start there. It's not necessarily going to pull somebody who's number 49 in the list, in the data, right? It's just going to start there, okay? And then it's going to go ahead and just draw its first one from there, okay? All right, so we're going to create a population of size 100,000. So we're going to say it has 100,000 people in it. All right, and then like I said, we need to create 4 variables. All right, so I have 2 quantitative variables here, so very generic names. If you want to give these more meaningful names, go right ahead. I always encourage you to do that. All right, but try to leave the numbers just as they are. Okay, leave everything else just as it is here. Okay. All right. All right. So for the first variable, quant1, we're going to tell SAS, give us a normal distribution with a mean of 100 and a standard deviation of 20. Okay. For the second quantitative variable, again, a normal distribution. It also has a mean of 100, but look at the standard deviation. All right, it's 200. Okay. Now, like I'll say later on in the lectures, when you have a standard deviation that is as large or larger than the mean, okay, you have a whole lot of variation in that distribution, okay? A lot of variation there. All right, so in this case, what this effectively does is that it creates uncertainty about any estimate that you get, okay? So you might have an actual estimate of I don't know, you might get an estimate of 50, but if you run the sample again, maybe the next time you have an estimate of 100, and then if you run it again, maybe you get something like 0. Okay, so when you have a variable that has such a large standard deviation, relative to the mean, right? That can be problematic. Okay, so that's something you always want to keep in mind, and that becomes a really important point when we start talking about evaluating estimates that we get and evaluating samples, right? The quality of those things. All right. For the first categorical variable, we're just going to set up a simple table statement. Here we only have one value, but of 0.5. But just keep in mind that if you only put one value in the table statement, SAS will automatically adjust for the second value. All right, so since I give it a value here of 0.5, it's going to automatically make the other value 0.5. Okay, right, because everything has to add up to 1. All right, so for this first categorical variable, right, it's going to have 2 values, right? Those values are going to be 1 and 2, and we'll just kind of, do a little bit more to add some context to those values, all right, to add some metadata. All right, and then here for the second categorical variable, also using a rand table statement, all right, and here we say, all right, well, one value is only going to occur about 1% of the time. Okay, so I'm going to occur about 1% of the time. Everything else, the other value is going to occur about 99% of the time. Okay. So this first value would be 0.01. The second one would be 0.99. Okay. All right. Now, the reason why I do this is because uh, even with random sampling, right? Even with random sampling, uh, uh, just by virtue of that one value occurring so infrequently in the data, sometimes that screws up your ability to get a good estimate. Okay. All right. Um, so we'll see what it does here, but that's something else that you want to keep in mind. So up here for quantitative variable 2, you want to remember a large standard deviation, large relative to the mean. Okay, that can be problematic for getting a good estimate of what the population actually looks like. Okay, here also, right, for the categorical variable, when you have um, one value that occurs, 1% of the time in the population, it's going to be kind of difficult to pick up that value in your estimates. Okay, right? Hey, think about it like this. Well, I mean, the numbers that occur the most frequently in the data, all right, well, those are going to be easy to pick up through random sampling. All right. Uh, Numbers that occur infrequently, like we have here, numbers that occur infrequently are going to be almost by definition, much more difficult to pick up in a sample. All right. And in some cases, we might miss them completely. All right. So uh, that's something else you want to keep in mind. Okay. Okay. So after you have created your data, go ahead and include a proc format statement. Um, and again, it's just to give the categorical variables. We'll apply this format to the categorical variables just to kind of give them a little less of an abstract feel. Okay. Just like I said, you want to use the proc format statement to, kind of give some context to the values that your variable might take on, certainly to any categorical variable. All right. So you want to go ahead and just set that up, and then move on with, let's just move on with the rest of the program. Okay, to draw the sample, we're going to use Proc Survey Select. Now, there are a number of different functions this procedure can carry out for us. All right, but we're only going to use it to draw a sample from the population. All right, so we're going to tell it, go back into our pop data set, okay, and pull a sample from that data set. All right, and we want you to do it like this. All right, so all these options that we have following proc survey select, data equal pop data, method, reps, in, out, um, all of those things tell SAS, you know, how to pull the sample from the population, and then, um, what to do with the data after it creates it. Okay, so uh, we have data, pop data. So we're telling SAS when it starts this procedure, go into the population data set, all right, and then draw a sample using the method of simple random sampling. Okay, so SRS stands for simple random sampling. All right, and that's so it's going to set up a selection mechanism that says, all right, well, give everybody the exact same chance of being selected into the sample. Okay. All right. When we go to reps 1, this is telling SAS that we only want it to pull one sample out of the data set, out of the POP data set. All right. And we want that sample to have 30 people. All right. So now remember, the population has 100,000. We set up a population of 100,000. Okay. Um, but here we're telling SAS, all right, well, just get 30. Okay. So you want to remember, folks, you want to remember what you've been learning over the last, couple of lectures here, right? Bigger is better. Bigger sample is a better sample. Okay. But even in some of these small samples, sometimes we can get it right if we do a good job of pulling the sample from the population. Sometimes just a very small sample might might give us some insights. Okay. Uh, but also keep in mind, well, what would be the overall quality of the sample? What would be the overall quality of your estimates? Okay, so we'll talk about that a little bit. All right. This last option, out equals SAMP data, this is telling SAS, okay, so once it pulls these 30 people from the population using a simple random sample method, create a separate data set that only has the information for these 30 people, okay? And we're going to call that data set SAMP data, all right? So population data, sample data, okay? All right, what is next? Okay, all right, so we're going to do proc means and proc freak on the population data, and then we're going to come back and do it on the sample data, okay? Because we want to be able to compare the mean for the sample to the mean for the population. We want to be able to compare the mean for the proportions. So, looking at the categorical variable, we want to be able to compare the proportions for the categorical variable in the sample to the proportions for the categorical variable in the population. Okay, so in order to get uh, the data, or in order to get the parameters for the two quantitative variables, we simply write proc means data equal pop data, and then we use the options. We say mean, standard deviation, and then standard error. Okay. All right. And then use the var statement, var, quant1 space quant2. All right. And that'll give us the means. All right. And then for the categorical variables, we want to use proc freak, data equal pop data, and then say, all right, here are the tables. All right. cat1, cat2. All right. Tables because it's going to display each value of the categorical variable. Okay. Rather than getting a summary statement like you do in with proc means. Okay. All right. So this gives us the population parameters. All right. Here we go to the sample data. Okay. So these are essentially the estimates of the population values. Okay. So we have data, SAMP data, mean, standard deviation, standard error. Okay. All right. So those are typically what we work with. All right. But we're going to do a couple of other things because we want SAS to generate confidence limits for us. Okay. All right. So here we have this option alpha equal 0.05. Okay. So this option means, right, that SAS is going to give us what's called a 95% confidence limit. All right. So that's going to allow us to say that about 95% of all observations, all right, in this distribution fall between these two values. Okay. All right, and those two values are the lower confidence limit and then the upper confidence limit. So just like we talked about in the lecture. Okay. All right. So that's for the two quantitative variables. Now, for the categorical variables, we have to do something a little bit differently. All right. So again, we're telling SAS, take a look at the sample data, right? Give us the tables again for categorical variable 1 and categorical variable 2, right? But then we want it to give us the confidence limits for each of these values, all right? So for each of these variables, all right? So we're going to say treat it as binomial data, all right? And that's what both categorical variables are, right? They are binomial variables, right? They only have two values, all right, 1 and 2, all right? And then, we're saying here with CL, produce the confidence limit. So it's going to automatically give us the 95% confidence limit for each of the variables, okay? All right, just going back up here one thing. If we didn't have alpha equal 0.05, SAS would automatically default to the 95% confidence limit. Okay, I just wanted to show you this one, show you like this, because again, you're going to be seeing quite a bit of this from in the next two chapters. Okay, that's when we'll really get way deeper into what alpha means. Okay, but for right now, just remember that alpha equal 0.05, right, is going to set up a 95% confidence limit for us. So whatever estimates we get from the samples, right, SAS is going to compute the confidence limits based on those, based on the sample data, and then it's going to say, all right, there's a 95% chance that all of the values in the sample fall between this value and that value. Okay. All right. Let's go to the next one. All right. So here's the output that you'll get from the survey select procedure. All right. It'll give you, quite a bit of information, but you should be able to follow it pretty well here. All right. So the selection method, simple random sampling, right? So SRS, simple random sampling, right? The input data set is the population data, right? Here's a random seed number. So it started with, we gave it the number 49, all right? And then it jumped to another seed value, right? Which is, what's that? 712,574,831. Okay, so we just need to give it a starting point, and then it jumps to a random seed value and goes from there. Okay, but we just need to give it that initial starting point. All right, so the sample size is 30, which means the selection probability, all right, is 0.3. All right. We won't worry here about sampling weight. Okay. Number of replicates, 1. Total sample size, 30. Right. And then the output data is the sample data. Okay. Okay. The next set of output you should get after you run your program is the Proc means procedure and the Proc freq procedure. And the first set of output would be for the population. All right, so this is for the Proc means and Proc freq on the population data. All right, so like we said in our program, in our data step, we want the variable quant1 to have a mean of 100 and a standard deviation of 20. So that's pretty good. SAS delivered on that. We wanted quant2 to have a mean of 100 and a standard deviation of 200. So again, very good. All right. For cat1, we wanted that to have a fairly even split across the categories, about 50% here and about 50% here. All right, and so again, that's looking pretty good. All right, and for cat2, we wanted to have a pretty disparate distribution where the value yes would occur only about 1% of the time, and the value no would occur roughly 99% of the time. So again, this is looking pretty good. All right. Okay, so here's where we start taking a look at our sample data. Okay, and already you have some pretty worrying problems here. Okay, all right. So for quant1, right, it looks like we get a pretty good estimate. All right, the estimate or the population parameter was what, 99, something like that. Okay, and the standard deviation was, very similar. All right, so we have 102.16 and then 19.68 for the standard deviation. We have a standard error that's nice and small relative to the mean, right? Far smaller than the mean. Okay, and that in turn gives us a pretty good interval. All right, so the lower confidence limit is 94.81. The upper confidence limit is 109.51. All right, so this is saying that if we were to go back into this population and get 99 more samples, so we'd have 100 overall, at least 95% of those samples would fall within this interval, right? 94.81 and 109.51. Okay, and so one thing we want to do is just sort of step back here and say, all right, well, it looks like, right? It looks like this confidence limit contains the population parameter, right? Okay, so, but again, folks, just remember, and I'll probably say this a few times, during the rest of the lecture, all right? You want to remember that you don't often have, well, you rarely have knowledge of what the population parameter is, okay? Again, so here, since it's a simulation, we can do that, okay? But a lot of times, you won't have that information, so you wouldn't be able to make a direct comparison between, this confidence interval and, the population parameter, okay? All right. Well, one thing you can do is say, all right, well, let's look at the standard, let's look at the mean, let's look at the statistic, right? And then let's look at the standard error. And if the mean and standard deviation, standard error, if the mean and standard error are pretty close in value, all right, you're going to have this massively large confidence limit or confidence interval, okay? All right, and so, when you have this really large confidence interval, okay, again, it's telling you there's a lot of uncertainty. Your data has generated a lot of uncertainty about where that true population parameter might be, okay? About where it might be. All right. So take, for instance, quant 2. All right. So we have a mean of 27.9. Remember the mean, the actual mean that we got for the population parameter, I think, was 79. Okay. It has a standard deviation of 204. All right. And then it gives us this giant, standard error. So, the standard error is 37.31. The mean is 27.9. All right, so we have a standard error that is larger, and some might say considerably larger than the mean. Okay, and so again, it's just going to create these super large, confidence intervals. Okay, so then you go over here, you look at the confidence interval, and it says, okay, 95% of the samples, of the 100% samples that we pull out of the population, will have a mean for quant 2 that's anywhere from negative 48.42 to positive 104.22. All right, that's just way to hell too big. Okay, just a lot of uncertainty. All right, so this, to kind of illustrate what that uncertainty looks like, imagine this. So this is essentially saying that if you go back into this population, grab another sample, run the same analyses, you might come up with a mean that's, I don't know, 0, right? Which would still be way off. Or if if you go back in a third time, get another one, then maybe it's 100. You go back in again, maybe you get a mean of 85, something like that. All right, but it's just saying that it's very difficult with the information that it has here. It's very difficult to kind of detect that true population parameter, right? Or in this case, the mean, the population mean. Okay. All right. So just a lot of uncertainty, right, driving this. Lots of uncertainty. And again, it's chiefly the result of this. Okay. All right. So if you get, and of course, the standard error. Okay. So when you see something like this, it tells you that it's going to be really difficult predicting the true population parameter based on your sample data. It's going to be very, very difficult to do that. Okay, so if the standard deviation is large compared to the mean, or even larger than the mean, okay, you're going to have problems. If the standard error is also larger than the mean, again, you're going to have some major problems. Okay, right? Major problems trying to, come to some sort of confident estimate, right, of the population mean or just the overall population parameter. Okay. All right. So here's the sample output for the proportion. We're looking at the output for Cat1. All right. So it gives you the table up top, just a basic frequency table. So for Cat1, we had 20 people, 20 of the 30 people in the category yes, 10 of the people, 10 of the 30 in the category no. All right. So we had 66% here, 66 plus percent of the sample in this category, 33 plus percent of the sample in that category. All right. So again, we set up Cat 1 to give us a 50-50 split, right? And then the population data, it gave us something really, really close to the 50-50 split. All right, but here we have something that's, sort of far removed from that, okay? All right. Uh, Now, to get the results that you're looking for your table, you want to just come down here, all right, to the to the top section of this binomial proportion table, all right. So notice it says cat1 equals yes. All right, so this is just talking about the proportion for one of the values, right? And in this case, it's just looking at the value yes. All right, so it's just analyzing that particular outcome. All right, we could tell SAS with a simple change in the program to select no as the focal value, but it will automatically just take the value with the value for the variable that corresponds to the lowest numeric value. All right, so here yes corresponds to a numeric value of 1, right? No corresponds to a numeric value of 2, right? So automatically it's going to take yes because that corresponds to a numeric value of 1, the lowest numeric value. Okay. All right. So then it reports the proportion, 0.66. So it just takes this value up here, 66.67, right, and divides it by 100. Okay, and that gives us 0.6667, right? ASE stands for asymptotic standard error. Okay, so it's the same standard error that was computed in the slides for chapter 2, or not for chapter 2, but for part 2 of chapter 7. Okay, all right, and that gives us a standard error of 0.08. All right, which is obviously much smaller than 0.67, but that's still a fairly large standard error for the variable. Okay, all right, and so it also reports the 95% confidence limit again just for this value. All right, so it says, all right, well the true population parameter would be anywhere between or if we were to go back and pull 100 samples out of this population, all right, that at least 95% of those samples would fall between a value of 0.498 and a value of 0.835. Okay. All right, but we know, because we're running a simulation, we know that the value is actually closer to 0.49, right? The true population parameter in this simulation is 0.4994, something like that. Okay? All right? But again, that's a really large interval, okay? And it makes us a little suspect. All right? It makes us a little suspect of what's going on here. All right? Let's see. Is there anything else I want to say about this? No. All right. So, you can take a look at some of this information here also. Exact confidence limits are, you interpret them the same way, right? But there's a different set of mathematics that go into calculating that limit. Okay. So here we're just going to stick with the simpler stuff. All right. We'll just stick with the simpler stuff here. All right, so here's the output for cat2. All right, so we get a distribution that is more like the distribution we set up in our data step. Okay, so we get 3% of the sample in the category yes, and then we get 96.67% of the sample in the category no, right? So this is the split we designed, okay? All right, So when we go down here to the binomial proportion table, right, again, we're looking at cat 2 equals yes, so we're just looking at that top category, right? So for the proportion, it gives us 0.033. So again, it just takes 3.33 and divides it by 100 to get the proportion, right? The asymptotic standard error is 0.0328. And again, you know, it's pretty well matched up here. Okay. Again, that's a little problematic. Okay. When we go on to calculate the 95% lower confidence limit and the 95% upper confidence limit, we get values of 0 and 0.0976. Okay, so roughly 0.10. All right, so again, it's still a pretty large interval. Okay, sorry about that. I don't know why it took me so long to get interval out of my mouth. Okay, but it's still a pretty large interval. Okay, yeah, on the one hand, it does contain the population parameter. Okay, but on the other hand, there's still a lot of uncertainty, right? If we were looking at this without knowing the population parameter, right, we would have a considerable amount of uncertainty facing us, okay? Right? Because it could be the population parameter might be might be 0, or it might be 10 points or more higher than that. Okay. All right. So let's go on. All right. So when we're reporting the results, you want to use a nice sort of device to summarize the results. Okay. So you don't need to report every single statistic. All right. You just need to kind of report those statistics that give the reader a really nice summary of what you found. Okay. All right. So you want to also make sure you include information that will allow the reader to make some assessment, to make a reliable or accurate assessment of the quality of your data, okay, and the quality of your results. All right. And so, okay, I was thinking something else was coming up next. All right, but anyway, um, so the first part of the first thing you want to do is report the results, but then you also want to evaluate it. Okay, so the question they're trying to answer is how reliably does the sample represent the population on the different variables, right? So we have 4 variables. How well does it do on those 4 variables? All right, and when we say reliability in statistics, this is sort of what we mean. All right, reliability is assessed by the probability of getting the same result if additional samples are drawn from the population using the same method. Okay. All right, so if we went back and got sample after sample after sample using the same method of randomization, getting the same sample size, right? How likely is it that we would get this exact same result? Okay. All right, and to evaluate or to answer this question, all right, we want to take a look at the standard error for the variable, and we want to ask, well, is it equal to or larger than the sample statistic? Okay. And I think in the table I have it set up a little bit differently here. I ask if the standard error is smaller than the sample statistic. Okay. All right. But you want to ask a question like that. You want to make some sort of comparison between the standard error that you compute, that SAS computes, and the sample statistic. Okay. If those two things are close in value, that means you're probably going to have a fairly large um, interval, right? And that means that it's going to be much more difficult for you to kind of estimate what that true population parameter is. Okay, all right. Um, and then you want to look at the population, since we have it, right? We want to compare the population parameter to the 95% confidence interval. And we ask simply, all right, does our population parameter fall within that confidence interval that SAS has computed for us? All right, but again, right, you rarely have the population parameter, so you're relying most on this one, all right, on this one evaluation criteria. Okay, you're relying mostly on that one. But since we have the true population parameter, we'll go ahead and include this one as part of our evaluation criteria. Okay. All right. So just to kind of give you, to hopefully give you a little more sense of how this evaluation criteria plays out. All right. So we have the question about the standard error over here, right? Is the standard error for the variable smaller than the sample statistic? Okay. Yes, no. Does the true population parameter fall within the 95% confidence interval? Yes, no. All right. So you only have what would be considered a reliable sample if you meet this condition. Okay? If you answer yes to this, okay, and yes to the population parameter falling within the 95% confidence interval. All right? This is the only condition under which you can say you have a reliable estimate. If you have any sort of other combination, so yes, the true population parameter falls within the 95% confidence interval, but no, right? The sample is not, the standard error is not smaller than the sample statistic. All right, then you're looking at an unreliable estimate, right? Yeah, it falls within the population parameter, or the population parameter falls within the confidence interval, but if you were to go out, to the population again and grab another sample using the same methodology, maybe you come up with a different, confidence interval, right? One that doesn't contain the population parameter. All right. So again, if having an answer of yes on one but no on the other, just that doesn't help you. Okay. So if we go yes, the standard error is smaller than the sample statistic, but the true population parameter does not fall within the confidence interval, right? Generated by that standard error, or generated in part by that standard error. Again, you're looking at an unreliable sample estimate. Okay, so a reliable sample estimate here if you have yes on both of these. Okay, and on anything else, right? You have to treat the sample as, or the sample estimate rather, as unreliable. Okay, and of course, if you have, if you score no, all right, if you answer no to both of these questions, then you're looking at tons and tons of uncertainty, right? Let's see, is there anything else I wanted to say about that? No, I think that was it. Okay, so now, so we spent that time evaluating the estimates, but now you want to evaluate the sample, okay? So here you want to say, all right, it's an excellent sample, or it's highly reliable, if 100, percent of all the sample estimates meet the evaluation criteria. Okay, right? It, it starts falling. The sample starts falling into the mediocre range uh, as soon as it hits anything less than 100%. All right. So you might think, well, that's kind of harsh. If it drops just 1 point to 99%, it's now a mediocre sample. All right. Other, you might see some variation in this evaluation criteria across, statisticians. Okay, so you might come across some statisticians that say, well, 99%, that's still good. 95% or higher, that's still an excellent sample. Okay, um, I try to go much more conservative. All right, because of the type of data that I work with. When you're working with data that's based on human behavior or human perceptions or something like that, human opinions about things, um, you're already dealing with a lot of uncertainty, right? Even before you uh, go get a sample, you're already dealing with a lot of uncertainty. Okay, because you're dealing with things that can change radically, like opinions, a person's opinion. We talked about it in one of the last lectures, right? Um, a person who has an opinion of you know some person or something or whatever, well, their opinion about that person or thing might change even as you're asking them the question. What do you think about this person or this thing? Right? Their opinion might change as they're listening to you ask the question. All right? So, you there's a lot of uncertainty. So you'll find that a lot of behavioral and social scientists um, take a pretty hard conservative, you know, um, approach to evaluating the quality of their sample. All right, they hold a very high standard for considering a sample to be an excellent sample. Okay, all right. So mediocre sample, pretty much anything from 80% to 99%. Okay. Poor sample, anything less than 80% of the sample estimates meet the evaluation criteria. Okay. All right. So now I think we're ready for the table. Okay. All right. So here's one way to lay out a table. All right. Um, Once you get into your research methods courses and you start looking at, when you start looking at um, published papers, published journal articles, you'll see that some folks set up the table a little bit differently. Okay, so here's one way to do it. Okay, but whatever method your professors tell you, all right, and just stick with that method. Okay, so again, when you get into your major classes, you'll see tables set up differently. So you just want to be familiar with how tables are set up in your major. Okay. All right. So anyway, um, when we take a look at the table, all right, we're laying out the population parameter, the sample estimate, all right, then we're looking at the standard error. This is for the sample. This is based on the sample, right? Then we're looking at bias. So what we're doing here is taking the sample estimate and subtracting the population parameter, okay? Such that if we get a negative value, we know that the population, I'm sorry, we know that the sample estimate is lower than the population parameter. If we get a positive result, right, we know that the sample estimate is larger than the population parameter. So when it's negative, the sample underestimates the true population parameter. When it's positive, it overestimates the true population parameter. And of course, if it's zero, you know, it's the sample estimate is exactly the same as the population parameter. Okay, but this is what we mean by bias. You know, how far is, and in what direction is the sample estimate relative to the population parameter? How far does the sample fall from the population parameter? All right, and then we have the lower 95% confidence limit for each variable, and then the upper 95% confidence limit for each variable. Okay, so now remember the two criteria, okay, for evaluating the estimates. Okay, all right. Is the standard error smaller, right, than the sample estimate? So here we say yes, okay, right? And so we can see our sample standard error is way smaller than the sample estimate, all right? And so again, folks, you want to remember what this means, right? It means that if we were to go pull, you know, additional samples, all right, almost all of those samples would have this value, 102, or something really close to it, okay? All right, so if when we go to the next question, right, does the confidence limit contain the population parameter? We say here, yes, okay? So yes, it does, okay? All right, so the estimate for quant 1 looks pretty good, okay? It looks really, really good, all right? So we would say this is reliable. All right, we would say this is reliable. Okay. All right, so for quant 2, all right, the population parameter is 79.09. The sample estimate, though, 27.9, so way off. Okay. The standard error, all right, is actually larger than the sample estimate. So that's a bad thing. Okay. That looks awful. All right. And then we get this, we get a confidence interval that does contain the population parameter, so that's good. But again, you know, you want to say, no, this one thing is off over here. This one thing is off. So we need to say that's unreliable, right? It's an unreliable estimate that we get. Okay, it's an unreliable estimate. All right. So for CAP 1, all right, we have well, we have but we meet both conditions. All right. So our sample estimate is 0.67, right? Our standard error is 0.09, so it is much smaller than 0.67. So that's good, right? So it means that you know, if we were to go back into the population and get more and more, you know, samples, right? We would get something kind of in this range, right? But you know, we could possibly pick up 0.54. Okay. All right. Bias is a little bit large, so that's concerning. All right. But the confidence limit does, the 95% confidence interval does contain the population parameter. All right, so, you know, there are a couple of things worrying about the estimate, but we would say, all right, based on those criteria, all right, yeah, it's a reliable estimate. Okay, it's a reliable estimate. All right, so here for Cat2, right, got the population parameter, we have the sample estimate, but then the standard error is the same as the sample estimate, all right, which again is going to give you, so you should be prepared to see a fairly large confidence interval. So the lower confidence limit is 0, upper confidence limit 0.10, again as we saw on the previous slide, or in one of the previous slides. All right, that's a fairly large interval. Okay, all right, it does contain the population parameter, right, 0.02. It does contain the population parameter, but still, you know, this is going to generate some uncertainty for us. Okay, this is going to generate some uncertainty. So we would conclude that the sample estimate for Cat2 is unreliable, all right, based on those criteria. All right, so then how would we evaluate the overall sample? We'd say this is a poor sample, poor quality sample. Okay, this is a poor quality sample. We need to try something else. We need to try a different method. So instead of maybe simple random sampling, we go with something that's called stratified random sampling. All right. We didn't go into it here because chapter 7 already has so much stuff, right, to cover. All right, but it's possible that in your research methods classes you'll learn more about you'll learn more about simple random sampling, and you'll learn about stratified random sampling. All right, so but anyway, it's a poor quality sample what we have here. We might try a different method of sampling, and certainly a different random sampling method, I should emphasize. Right? We don't want to go to non-random sampling because that's just going to make the problem worse. All right? And we want to kick up the sample size. All right, so our sample here was based on the sample size of 30. All right, maybe that's just too small. All right, maybe we kick it up to 300. Okay, maybe we kick it up to 500, or maybe just 100. Maybe 100 would just do very well for us. Okay, we don't need to go get all 100,000 people in the population, even though that would be ideal, but a lot of times we can't do that. All right, but we should bump up the sample size. Okay, all right. Let's see, what else do we have here? Okay, so your assignment for Lab 7. All right, you can do things just as I set it up in the previous slides, right? Create a population consisting of 4 variables. You want to create the population size at 400,000, okay? Just set it at, I'm sorry, not 400,000, 40,000. Set it at 40,000. Or if you want to go 400,000, go ahead and do that too. All right. The variables, you can make them all quantitative variables or all categorical variables, or come up with some combination, some sort of mix. That is completely up to you. You want to draw just one sample of 400 people, okay, from that population. So essentially you're drawing 1% of folks from the population of 40,000, right? You're drawing a 1% sample. All right. You want to then, just like we did in the slides, you want to compute the population parameters first. Then you want to come back and compute the sample statistics. Then you want to construct a table, and you can follow the one exactly like I have in the slides, right? And then you want to give an evaluation of each estimate as reliable or unreliable based on the criteria, right? And then you want to give an overall evaluation of the sample. Is it an excellent sample, mediocre, or poor? Okay. Now, some of you, right, are going to get excellent samples, right? Only a few of you should get something that's either mediocre or poor, okay? Um, you there's a probability. It is possible for maybe a few of you to get poor samples. But if you end up with that, that does not mean you've done a bad job with the lab assignment, okay? It just means that you were, by random processes, you ended up with this sample, okay? So if you get something mediocre, don't worry, okay? Just go ahead and put, yeah, this is just a mediocre sample. That's not going to be your grade for the assignment. Just like poor, getting a poor sample will not be your grade for the assignment, okay? It's just what you got, okay? And then I haven't set up the Dropbox yet, but when you submit it to the Dropbox, you want to, show me a copy of your SAS program. You can just take a screenshot of it, or copy and paste it into a document and upload it. You can do the same thing with your table. Well, for your table, you have to create that in Google Docs or Microsoft Word or some other word processing program. Okay, so but after you set that up and fill it in, go ahead and upload that, and then you want to write out your evaluations for the estimates and for the sample, right? Maybe just right under the table. Okay, again, just following, word for word what I wrote there. The sample estimate is, whatever. The sample itself, the quality of the sample is, boom, whatever. Okay, so if you need any help, doing this, please let me know, all right? I've worked with a few folks already, not on this particular assignment, but I've worked with a few folks already on different things. All right, I don't mind helping you. All right, again, my main goal is to get you ready for those next courses, All right, that is my main goal. Okay. Let's see, and I think that's it. Yep, that's it. Okay. So again, let me know if you need some help, all right? Okay. Talk to you later.